In this course, we have discussed the impact of changes in greenhouse gases and changes in albedo due to ice, snow and clouds on the Earth's climate. In addition to these, there is one more effect which we will discuss now. This is due to small particles which we cannot see, and they are called aerosols. And they can change Earth's albedo, that is the reflectivity to solar radiation, or the amount of radiation absorbed. Now, this is more complicated than what we discussed in the case of carbon dioxide, because aerosols, their abundance varies a lot both in space and in time. Okay? It depends on season and it depends on where you are. In urban areas, there is much more aerosol than in forests, for example. So, we do not have sufficient data to accurately model aerosols, but we have to do it because it has an impact on Earth's climate. Other complication of aerosol is it comes in variety of forms. Carbon dioxide is only one molecule. It does not react chemically. Its concentration is almost uniform around the Earth, and it is uniformly mixed in the vertical. But aerosols, which are released at the surface primarily, both by natural processes like winds or volcanoes, or by human industries and human actions. Now, these aerosols come in variety of forms. They have different chemical composition. Carbon dioxide has only one composition, CO2, and it does not change, it does not react. But aerosols can change, aerosols chemical composition can vary. So, this is a very tough subject which has been tackled only in the last 30 years. So, we will talk about it and point out the kind of uncertainty that comes in our ability to predict climate change on account of aerosols. Okay. Now, here are the range of particle sizes that you encounter. Very small particles called Aten nuclei, and there are large particles and giant particles like dust. Okay. Of course, there are aerosols due to cloud, liquid water is also an aerosol, ice, okay. And of course, they also are involved in generating lightning and electricity. They affect the radiation that is scattered and absorbed in the atmosphere. They affect the chemistry and air pollution. So, they do a number of things, but our focus is only on its effect on climate. And its range of sizes is from 10 to the power of 4 micron to 100 micron range. Okay. And we will focus on particles in the range of 0.2 to 1 micron, which affect the solar radiation. Now, here is a comparison between the size of a human hair, which is around 60 micron, compared to a typical particle of soot, which is around 10 micron. So, the soot particle is much smaller than the size of human hair. The other particles like sulfate and particles emitted by a diesel engine, they are even smaller. Okay? And they are of great concern to human beings because they affect our health. These particles, when you inhale them, they affect your lungs. Okay? There are various health complications that occur due to inhaling small particles. But we will focus mainly on climate, which is the factor which is influenced by large particles. Okay. So, aerosols play an important role because they modify the global radiation budget directly by scattering the photons either upwards or downwards, or by absorbing the photon and converting into heat. Okay. they can also indirectly affect our climate by altering the cloud. These aerosol particles are the particles on which water vapor condenses to form a liquid droplet. So, if there are a lot of aerosols, it will affect the number of liquid particles in the atmosphere. Okay. So, we have to worry about both the direct effect aerosol has through the radiation budget and the indirect effect it has by modifying clouds. Okay. Both these are critical, and our understanding of the direct effect is quite good because that occurs under clear sky, but the impact of aerosol clouds is very complicated, and we already saw that our ability to model clouds in climate models is limited because of the grid size that we use in these models. Now, aerosol is going to affect the clouds which are not properly modeled. So, it is a very great concern for uncertainty in modeling. Now, let us look at typical aerosol optical depth, which is the integral of in the vertical of the extinction coefficient, which is the sum of scattering and absorption. When you integrate vertically, satellite can measure the aerosol optical depth at the top of the atmosphere. Okay. And what it shows is globally the mean aerosol optical depth is around 0.06, okay, quite small. But if you look at land, it is much larger, more like 0.14. So, in the land the size of the particles are larger. Land is a major source of aerosol particles, and if you look at our ocean, it is more like 0.03 micron. So, ocean produces aerosols due to wind acting on the ocean and the salt particles which come out, they also produce aerosols, but they are, and ocean has dimethyl sulfide which produces sulfate aerosol, but they are smaller in size, around 0.03 micron. So, we have a whole range of sizes here, from large sizes over land, somewhat small sizes over ocean, and the global average is around 0.06 micron. Now, the concentration of particles has been measured by satellite, and concentration of particles the size of 2.5 micron is shown here in terms of microgram per meter cube, the amount of particle. And this is annual mean for the year 2002, and you see the highest amounts are in the Indo-Gangetic plain and in China. Okay. And there is not much data over Sahara, because Sahara is a very light desert where it is not easy to measure, and also over ice. So, you see that the number of particles over ocean is quite small, in the range of 5 to 10 micron per microgram per meter cube, while over land it is much higher, it is more like 10, 20, and highest value is around 40 over China. Okay. So, you see a whole range of sizes of particles varying spatially a lot between ocean and land, and even within land. Okay. So, this is what complicates any attempt to understand the impact of aerosol on climate. Now, aerosol comes in various chemical forms. There are sulfate, which comes from emission of sulfur dioxide by industries. There are nitrate, which comes from fertilizer. Sea salt comes from the ocean, evaporation, and when a drop evaporates, the salt particles come out. Most of these are which scatter radiation mostly, okay? And the scattering effect is the strongest at short wave, where the solar radiation is incident, and is much smaller in the longer wavelength. Okay? Except when talking about large particles, then they also will absorb in the infrared. So, scattering by aerosol increases the fraction of radiation reflected back to space, and hence it cools the earth. So, primary role of aerosol is cooling the earth, but there are black carbon aerosols, which we call soot in common language. They absorb solar radiation and they contribute atmospheric warming, but they cool the surface because they block the solar radiation. Now, if these black carbon aerosols are located above the cloud, they will enhance absorption, and they are above snow and ice, also they will enhance absorption. But if that black carbon aerosol is below the cloud, it can do nothing. Okay? So, you can see that it is important to know where the aerosol is with reference to cloud. If it is above the cloud, there is one kind of effect. If it is below the cloud, it is different. So, aerosols not only impact climate, they also impact our health. As already pointed out, when we inhale these particles, they cause a lot of problems in our lungs. They also affect agriculture, because a lot of dust settles on a leaf. It will block the pores of the leaf and it will affect photosynthesis. And aerosol have also effect on the monsoon, because they alter the amount of radiation absorbed by the sun, and they also affect the clouds. So, both affect the monsoon. We will discuss the effect on monsoon in a later lecture. Now, here is a cartoon showing the different ways in which aerosol affect the atmosphere, and you can see there is direct absorption, okay, and it also can scatter radiation. It can affect the cloud condensation nuclei, that is, particles on which the vapor condenses. If you have produced a lot of aerosol particles, they increase CCN and thereby affect this one. And when these dust aerosol fall on the ocean, they affect the amount of phytoplankton in the ocean. Okay? And if they deposit over snow, and if they are black carbon aerosols, they will melt the snow quickly. Okay? So, there are lots of processes that are going on that aerosol has with cloud, with surface, with atmosphere. So, the impact of aerosols on climate is complicated. Okay? Most aerosols cool the atmosphere because they scatter the sun's radiation. Some aerosols heat the atmosphere but cool the surface. And in contrast to carbon dioxide, which we have studied in great detail so far, aerosols are not uniformly mixed. So, their impact is highly variable in space and in time. Now, aerosols are created naturally by dust where there is no vegetation, and by volcanic eruption, which occurs occasionally, and salt, which comes out of the water evaporating from the ocean. But in the last 100 years, the human induced sources are more important. They are sulfate coming from sulfur dioxide released from industrial combustion process, nitrates from fertilizer, organic carbon from various processes that take place in vegetated surfaces, and black carbon which comes from combustion. Now, I want to show you the seasonal variation of aerosols. Natural is shown in blue, and in red dotted is the anthropogenic, human induced. Okay? you can see they are out of phase. During the monsoon, when the wind speeds are high, the natural aerosols dominate. Okay? While in the pre-monsoon and the post-monsoon season, we have the domination of human created aerosols. Okay? For example, in North India in winter, there are a lot of aerosols released by combustion and other activities, and in winter the temperature variation in the vertical near the ground is different from normal. It increases with height, normally it decreases, and that is called an inversion. That inversion traps aerosols released by human action, and that is why aerosol is very high in winter in India, and this is data taken over India. And during the monsoon, the human induced aerosol comes down to around 30%, while natural aerosols increase by 70% because of the high wind during the monsoon season. Okay. Now, the important thing about aerosol, which makes it very different from carbon dioxide, is the lifetime. Okay. The residence time of a large aerosol like dust may be around 10 days. Okay. The smaller aerosol remain longer, and they may remain for 23 days. Okay. If you take a typical raindrop, which is of the size of a millimeter, 1000 micron, it remains only for a few minutes, it drops down. Okay. So, you can see that depending on the size of the aerosol, the residence time can be anywhere from minutes to 3 weeks. That is how long it remains. In contrast, carbon dioxide remains in the atmosphere for hundreds of years. So, this big difference between aerosol and carbon dioxide must be understood, because carbon dioxide impact is long term, aerosol's impact is short term. So, to again reinforce the idea, lifetime of the aerosol typically weeks, carbon dioxide hundreds of years. Chemistry of aerosol very complicated, depending on sulfate, black carbon, and various kinds of combinations. Carbon dioxide has a known chemistry, it does not change. Spatially, aerosols are non-uniformly distributed, while CO2 is uniformly distributed. In time, aerosol concentration varies a lot between monsoon and winter. CO2 shows a seasonal variation, but it is highly predictable. Aerosols can either warm or cool the Earth's climate. Carbon dioxide can only cause warming. Now, IPCC has given this information about our understanding of various greenhouse gas and aerosols. Well mixed gases are well understood what they do. There is a high agreement between different models, and our confidence is very high. Okay. Same thing about ozone in the troposphere and stratosphere. Okay. When you come to water vapor from methane in the stratosphere, agreement is not so good because measurements are few, and confidence is somewhat lower than that of carbon dioxide. When you talk about aerosol radiant interaction, it's fairly well understood. Agreement is not so good because of the variety of aerosols, and the confidence level is high, but not as high as carbon dioxide. When you come to aerosol cloud interactions, very, very important. The amount of data we have is limited, medium. Agreement among different models is low, and confidence is low. So, you can see that the biggest problem we face today is we do not understand the aerosol cloud interaction well. So, this problem is still in the research arena, and will take a long time before we are able to understand the aerosol cloud interaction. Now, aerosol is characterized by its absorption and scattering properties, and the equation governs that. The equation of state, which we discussed a long time ago, shows that the rate of change of intensity of the radiation in the direction x depends on the intensity coming in, and it decreases depending on how much is absorbed and how much is scattered. Okay. Both scattering and absorption remove the radiation along the path of interest to you. In absorption, the photon becomes heat. In the case of scattering, the photon goes in a different direction, and the direction of interest to you, it goes down. Okay. Now, if you look at the estimate of the total amount of aerosol in terms of the aerosol optical depth, there are estimates from two different models, and you can see large difference in two different models used in the United States. The Goddard Institute of Space Science gives a very high concentration of sea salt, while the GFDL model in Princeton shows much lower value. Sulfate aerosol, GFDL indicates a much higher value than GIS. Dust, they are quite similar. Organic carbon, they are quite similar. Sorry, yeah, organic dust is similar, but GIS model has a bit of nitrate which is missing in GFDL. So, there are differences among models, mainly in terms of what they include or don't include, and this is one of the cause for uncertainty. Now, if you look at the measurement of the aerosols in different parts of the world, the single scattering albedo, which tells you how much of the radiation is scattered and how much is absorbed, is defined as scattered by scattered plus absorption. So, if the aerosol is totally absorbing like soot, then this will be 0, and if an aerosol is totally scattering, it will be equal to 1, no absorption. Okay. So, the range is 0 to 1 for single scattering albedo. Now, the values typically in different parts of the world varies between 0.35 to 0.56. Okay. And this variation is on account of differences in amount of soot. In South America and Africa, you can see there is more absorption. So, SSA is this is only the optical depth here. We come to SSA here, single scattering albedo. It is 0.98 in North America, where it is mostly sulfate, while it is 0.9 and 0.86 over Africa and South America, where there is more black carbon, and also in Maldives. Now, here is a good glimpse of how aerosol optical depth and the single scattering albedo vary spatially as obtained from satellite. Okay. So, as obtained by satellite, you see that black carbon aerosol have a very low optical depth and a low single scattering albedo, where they absorb a lot. Well, sulfate has 10 times more optical depth, that means more sulfate, but they are almost all scattering. Okay. When you come to dust, its optical depth is comparable to sulfate, and its single scattering albedo is similar to sulfate. Okay. When you come to sea salt, its amount, optical depth, is little less than sulfate and is totally scattering. Single scattering albedo is 1. Okay. Then you come to organic carbon produced during combustion. Its optical depth is larger than black carbon, 10 times and outside 5 times, and the single scattering albedo is 0.97, similar to sulfate. Okay. And then you add all this, you get this around 0.1 aerosol optical depth and around 0.95. Okay. But you see there is a lot of spatial variation in the aerosol amount. Now, here we can calculate the aerosol direct radiative forcing in clear sky. So, you can calculate how much additional radiation is reflected by these aerosols when compared to an atmosphere without aerosol. The radiative forcing is the difference between the radiation reflected with and without aerosol, and you can see that various models estimate radiative forcing anywhere from minus 0.2 to minus 0.4, that is, they are mostly reflecting, they are reducing radiation coming into that earth. While you can see the other models here, these are from Goddard Space Institute, there are values as large as minus 0.6. Okay. And observation, mostly based on satellite, give a range between minus 0.5 to minus 1. Okay. So, there is a problem here that the different models do not agree on the impact of aerosol on the radiation budget. They give values anywhere from minus 0.2 to minus 0.6, and that is a large variation in the model estimate. Okay. So, as we already mentioned, I want to remind you that aerosol directly influence the earth climate by scattering the incoming radiation back to space or by absorbing such radiation, or indirectly by modifying the properties and lifetime of the clouds. Okay. Now, this is somewhat easier to calculate because it is under clear skies. This is more difficult because it depends on whether the aerosol is above the cloud or below the cloud, and in addition it also depends on how hygroscopic or hygrophilic the aerosol is. The aerosol attracts moisture or it repels moisture. They affect how they affect clouds. So, that is what complicates the indirect effect of aerosols. Okay. Now, one simple example I can give you, if the atmosphere was fairly clean, not too many aerosols, they will have large droplets. Okay. Now, if the atmosphere is polluted, then it will contain more ice particles, that is the small, these are ice particles, these are liquid particles. There will be less liquid particles, more ice particles, and so area covered by ice cloud larger. So, what aerosol does is, if you reduce the aerosol in the atmosphere, it reduces the number of, it increases the number of liquid droplets which finally convert to ice. So, it produces more ice particles. Okay. Of course, this depends upon the hygroscopic or hygrophilic nature of aerosol, whether it attracts water vapor or they repel water vapor. Okay. So, there are so many effects that they are given separate names. If the entire effect influences the aerosol number of drops of ice, is called the indirect effect. The first indirect effect is through the effect on radius of the droplet that occurs. The second one is through the influence on number of droplets. Okay. Both effects are there. Then aerosol absorb sunlight when they are absorbed in liquid water in the clouds, that is called the semi-direct effect. The dispersion effect is it changes the distribution of liquid droplet in the clouds. Okay? Not scattering absorption, but changes the distribution. And final effect is glaciation effect by converting liquid droplet to ice. So, you can see this is a very complicated subject, because aerosol can have the effect on clouds on the liquid droplet size, radius, number of ice particles, and size distribution. So, this is a very complex subject, and not many models are able to simulate the effect of aerosol on clouds properly. Okay? Now, whatever I told you just now is shown here in form of a cartoon. Scattering absorption under clear skies, which is very simple, the direct effect. This is the undisturbed cloud, and once aerosol affects it, it changes the cloud condensation nuclei. It can suppress drizzle. Okay? It can increase cloud water height. It can increase the cloud lifetime, how long the cloud stays, and the indirect effect through changes of ice clouds and liquid clouds. Okay. So, there is a whole assortment of effects aerosol as on clouds, and different models model it differently. So, there is large variation among models with regard to impact of aerosols on climate because of the aerosol impact on clouds. Okay. Now, here is an example where the aerosol number concentration is given in the x axis in particles per centimeter cube, and y axis is given the droplet number concentration. You can see different observations in different field experiments. You can see that by and large the droplet number goes up when you increase the aerosol concentration. This data is from Atlantic Ocean, this data is from Indian Ocean. So, there are differences between oceans about how aerosol impact the number of cloud droplets. Okay. Now, we will continue the discussion in the next lecture about the effect of aerosols. Thank you.